Thanks so much indeed. Thanks for the kind invitation, and thanks to the organizers for all the effort and sweat of setting up this beautiful workshop on quantum thermodynamics. And unsurprisingly, this is what this talk will be about in the specific flavor, not of coffee break, but of fundamental corrections to work and power in the strong coupling regime. So when speaking about work and power, presumably we are, I guess, at the heart of the matter here. And with fundamental, I'm already giving away that for most of the talk we will be concerned with basic questions of the field, although... Yeah, but I'm rather loud, no?
Record. Be careful what you say.
Very good. So with fundamental, I'm giving away that we're mostly concerned with basics of the field, although I will insist at the end of the talk that what we will see will have some experimental implications and may help to give some guidance towards thinking of the much needed more experimental explorations of thermodynamical notions in the quantum regime. So to state the obvious at such a meeting, that's the precise reason why we are here. I mean, there's compelling evidence that thermodynamic notions have to be carefully revised when not thinking of macroscopic devices and systems, machines, but where the miniaturization has kind of progressed in such a way that single quantum degrees of freedom matter and come into play, such as charged ions, cold atoms, and V-centers, and so on. Then you have seen and will see that in the setting, entanglement and other quantum correlations, fluctuations, expressions beyond first moments, various readings of beyond single shot settings, and what's less appreciated sometimes, limits to control that can be meaningfully imposed will matter in one way or the other. And then at the heart of the matter is questions how notions of work and power would be changed. In fact, the very definition of what work even is in the quantum setting is somewhat controversial. Look at me going on this, and we've already heard something about this this morning. What is a key question, to my understanding, is what the scope is to develop a theory of quantum thermodynamics in the first place, beyond specific models, as, of course, for a given Hamiltonian and a given setting, one can compute lots of things, and that's very cool, but ultimately, I mean, much of the power of thermodynamics over the decades stems from the fact that one can largely abstract from the nitty-gritty details of a specific setting. So one would like to have some sort of intermediate level where the quantum features are there, but one can somewhat abstract from the fine print of the specific setting under consideration. So we will hint at that on several occasions throughout the talk. Having said that, this will not be a review talk, although I'm much tempted to do so, but I will, for reasons of time and coffee break, as Martin has mentioned, put a very basic, super simple question into the center of things and meditate a bit at the end, namely, what happens when interactions will matter? That's presumably expected to happen when we have a small number of quantum degrees of freedom, and how one can include them after all. So the deal is, if we think of thermalization, the mental image that comes into mind is that we have some blob sitting there, and ultimately we will have some environment put into contact with this system, and if we then wait for long enough, the system and the system will eventually thermalize to the Gibbs state at that respective temperature. That's what thermalization is about. That's in the very ontology of thermalization, that if you have a system put in contact with a bar, then the system will just have its own Gibbs state of this respective inverse temperature. And obviously this is the focus of attention, say, in phenomenological thermodynamics, and when we think of isothermal processes or quasi-static processes, this kind of picture is kind of implicitly assumed, needless to say. In resource theoretic formulations, and I'm sure we will hear more about this later this week, one really thinks of thermodynamic blobs, the quantum systems in given thermal states as resource, and it's not so obvious how one can think of of interactions in this sense. So this is kind of explicitly inbuilt in the formalism to think of thermalization in this sense. So having said that, this in the setting where there's a small degree, a small set of quantum degrees of freedom coming together, this can be a very unreasonable setting, and that's clearly inappropriate in the strong coupling setting, which in turn is expected to be relevant when a small number of quantum systems come together and interactions will matter in one way or the other. So what presumably will happen if interactions matter is that not the system will be a Gibbs state in its own right, but clearly there's interactions. So what one would expect is that the global state would thermalize, including the interaction, and the reduced state would be just the reduced state of a global state reduced to the system as such. That's what one would meaningfully assume to happen or expect to happen in the setting of strong coupling. And for most of this talk, we will be just concerned with elaborating on the consequences of what happens if one has such a kind of strong coupling setting where the system doesn't thermalize, but thermalizes to kind of the reduced state of a global Gibbs state. And we'll ask like what implications such strong coupling would have to readings of the second law. Then we can ask how notions of work extraction would have to be modified, whether this is a feature, or a bug, or a burden in this sense, whether we can gain or whether this is a limitation. Then what power limitations or enhancements can be expected due to a strong coupling in this sense, and ultimately also how results, that's something that's rather close to my heart, how results on thermalization and equilibration come into play to capture such settings. So this is the main point of this talk, if time allows. I mean, there's the coffee break at the end. I might meditate a little bit at the end to see, as a kind of trigger for discussions over the coffee break, I will mention some other results on fundamental considerations that we have been concerned with in quantum thermodynamics, but also insist how these ideas, or what Gerald Gibbs or so on related to Jörg's work, could be seen as giving some framework to think of more reasonable experimental settings in which quantum thermodynamic notions can be tested in an experimental setting. But this would be at the very end if it goes with. Good. So this is this talk. So let's get going. So let's start with the procrastination. Namely, well, I mean, this setting of strong coupling thermalization that I've laid out is brutally plausible and obvious, so to say. Yet, to emphasize that at the beginning, this setting of systems strongly equilibrating in this sense can largely even be proven in a rigorous setting using ideas of equilibration and thermalization of out of equilibrium many-body systems. And the thing is that if one has a quantum system with local, like finite range interactions undergoing non-equilibrium many-body dynamics, and looks at like quench-many dynamics in this sense, one would expect indeed such a system to relax and equilibrate. And that may not be entirely obvious. I mean, of course, the entire system cannot equilibrate. It's a closed system after all, but what can be true, and this is what generically happens, is that for the overwhelming majority of times, the system would look perfectly as if it had nicely and smoothly relaxed to the infinite time average of the system. And here, I mean, this is a bit jargon. So here, in the specific setting, the right-hand side can even be refined. So for the experts here, the effective dimension can be bounded in the setting. So one would really know that for the overwhelming majority of times, such a system and bath would perfectly appear relaxed. So it would equilibrate, and this is probably true. And there's also compelling experimental evidence in several settings of cold atoms that systems would in time would nicely and smoothly equilibrate and relax to the time average. In this sense. So systems become stationary, but do they also thermalize in the sense? And here the answer is yes. That's one of the few settings where at least in the high temperature limit, this intuitive notion can be even made very precise and rigorous. And this is a combination of two insights in this matter. The one thing is that at high temperature, like there is a certain threshold temperature that's kind of in a way model independent, above which all correlation functions in a lattice, even generalized correlation functions, if interested ask me, would be exponentially decaying in the lattice as a rigorous version of a notion of a thermal correlation length, if you will. And this is the one insight, and then this can be combined with an insight that if you have a global state and a Gibbs state and would make a local perturbation somewhere, then for long times the system would re-thermalize and would locally be indistinguishable from as if the entire system had been in a thermal state altogether. So this together can be seen as, at least in the high temperature limit, showing that without invoking the famous eigenstate thermalization hypothesis, the system would indeed relax to the reduced state of the global Gibbs state at hand. So this, I mean, it's super intuitive, but that this strong coupling limit would be kind of happening in such a system altogether. Here, even in a precise and rigorous sense. Good. So protocols. So what protocols? Yeah.
To get a sense of strong.
Yeah.
What if I take V going extremely large? Is it still gonna hold, or where does the bound on how big V can be?
Oh, I mean, I think that this would, in fact, V can be arbitrarily large. That's not a limitation. In fact, this would be true even if V is very large. This doesn't have to be seen as a perturbation, although we will come to that later. Okay, this is not small but perturbatively small, but this setting would be, in fact, generally true. In fact, even for very, very large V, this would be right.
Yeah. You're saying that even if the eigenstates thermalization hypothesis is not satisfying, a system would always look like a thermalization.
Oh. I'm not saying, no, I'm not, this would be very strong. I'm not saying this. I'm saying that this type of argument would kind of formally, mathematically use a weaker reading where you don't expect individual many eigenstates to be thermal or locally thermal, but something weaker that only in expectation, a kind of typicality notion that microcanonical states would overwhelmingly look like thermal states. It's slightly weaker than eigenstate. But I mean, I'm not saying that the eigenstate thermalization hypothesis would not be true or would be implausible. I'm just saying that you don't need to invoke this to come up with this statement.
But is it also restricted to some particular observables which have some kind of macroscopic character? It's not for all observables of the system.
No, but indeed, it's true. It's true for, like, in particular for local observables that would sit in the system and in the vicinity of the environment. For all of them, it would hold, and that's what's at stake.
It's somehow known in the celebrities, in the field.
No, sure. I mean, this is not very. That's what I'm saying. It's not. It's kind of intuitive. Here, it's kind of a refined setting that you can really, in a precise sense, get a trace norm certificate how close you are locally in this sense. So that's a natural expectation, but now put on a rigorous footing. But I mean, as I said, this is a very natural setting.
So the idea of invoking typicality is just saying that most states that you set up would be like that, but you could still imagine that you could set up
Oh, no. This is just how the argument functions. I mean, the setting would mean that in trace norm you get this statement. Given that, you would become close to the reduced state of a Gibbs state. It's just this type of argument would go along this path, not invoking eigenstate thermalization, but there's no notion of typicality in the statement of the setting as such. I mean, it's a great discussion. Can I kind of meander some of this to the end, to not challenge the coffee break too much? But I mean, I think we have also prepared. So protocols. So we are thinking of protocols in the strong coupling regime. We are looking at kind of three ingredients to this. That's three ingredients that are reasonable and plausible in the setting. As the reasonable control one can impose to such a system, we can think of taking our system and putting it into contact with a bath, maybe strong contact, so that the expected work cost, and we are here in the sense of work in expectation. We discussed that also later, where the expected work cost would just be the expectation value of the interaction Hamiltonian given here, so we can switch it on and off. Then there's fast quenches. You can quickly and suddenly change the Hamiltonian of the system, like in principle arbitrarily, and ultimately you can equilibrate or do thermalization in the strong coupling sense, which would not come along obviously with a work cost because it's just a natural equilibration process in a sense. And a protocol would be an arbitrary sequence of that type involving such steps. And one can ask, how much work can one extract in such a strong coupling?
For step C, are you assuming that it comes to equilibrium, or can you just partially equilibrate it and then?
No, I'm assuming that this kind of notion will just happen. I mean, I've shown this for a long time, it will happen, but here I press a button, it will look as if it had thermalized to a global Gibbs state. So in this sense, I'm not looking at partial equilibration of this type, but this will just happen.
Okay.
This is also an interesting setting, but if you think of, for reasonable times, this will just happen, and probably so.
Okay.
Yeah. So how much work can be extracted? It's instructive to think how this works for weak coupling, to kind of see how this goes. In the weak coupling setting, we know that the optimal work extraction scheme involves 4 steps. The first one is you take a system and replace the Hamiltonian by the Hamiltonian such that the state given would be the Gibbs state of this respective Hamiltonian. Then you switch weakly on the interaction with the bath, arbitrarily weakly. You do an isothermal process and you switch off the interaction at the end of the day so that the expected work extracted would be nothing but the difference in non-equilibrium free energies, which can be written as relative entropy expressions that has been seen many times and also in the previous nice talk. So this is the weak coupling setting. So how does work extraction change in the strong coupling regime? Now, this is changed in this way that one can still find a bound. So the maximum extractable work in such a protocol would be of the types such that the optimal scheme is still of the analog of the type that he would bring it in contact with the system, would think of an isothermal process, would take the system out at the end of the day. But now the maximum extractable work in any of such schemes would be the weak coupling expression together with 2 further terms that again can be written as an expression involving differences of non-equilibrium free energy. So there's lots of free energies also in this talk, as kind of continuing the theme of free energies. And indeed, writing them as relative entropy expressions, as we've also seen in the previous talk, we see that these terms these penalties are positive, meaning it's a burden. You do less, there's less work you can extract from this. And the interpretation of the second term is that you take a system and if you put it into contact with the bath, there will be some energy dissipated due to the interaction with the bath, whereas the other term is the kind of the work extractable at the end, because your final state is not quite the right thermal state of the own Hamiltonian, but there's still the interaction with the system going on. And this is largest clearly if the Hamiltonian systems, the system Hamiltonian, are chosen in such a way so that the penalty is smaller, so that the extractable work is maximized in the set. So, question? Okay, so why is this interesting? It's interesting because one can go a long way of actually solving this problem in closed form, in full glory and analytically. Thing is, so here's the expression. When we don't look at this expression, what one can show is that this optimal point, the optimal Hamiltonian that would give rise to the optimal work extraction, can be formulated in a general fashion that would involve an integral that looks like an imaginary time expression involving the imaginary time I beta, where beta is the inverse temperature. And the nice thing about this is that this is not just an abstract expression as it looks like, but and also in arbitrary settings, all the degrees of freedom of the bath would matter, but in reasonable settings, in particular in high temperature settings, this idea of the locality of temperature I mentioned earlier could be invoked so that this quantity is actually computable in the sense it would involve the system and the coupling and maybe a couple of degrees of freedom of the bath, but not the rest of the bath. So one can actually compute this integral involving a small finite number of degrees of freedom, and what that's as close it gets to a general solution for arbitrary Hamiltonians of the weak coupling work extraction setting for arbitrary types of interaction. So this is so this can be kind of solved in a closed form expression, which is kind of
So I don't see why h in the above expression. Is the time?
X takes the role of h, and the solution is then called h. Bit of an unfortunate notation. But I mean, the point is that it's just the quantities that you want are just kind of integrals of like Hamiltonian terms evolved in imaginary time under another Hamiltonian. This is what comes out. And indeed, for high temperature, this can be computed only involving a small number of degrees of freedom. Yeah.
I thought you were suggesting at the beginning that maybe you couldn't deal with these things in the resource framework, or at least within thermal operations. But isn't this exactly the same framework where you are turning on some interaction? I mean, you're effectively, by bringing in strong coupling and then taking it away, you're basically starting off with the thing not interacting, making it interact, and then putting back again. So isn't this exactly the same kind of framework?
Yeah, I mean, this is a good maybe discussion at the end. In what way this would relate to kind of resource theoretical pictures. Indeed, it is. I mean, in a way, this can be partially used. I would even think of putting more meat into setting kind of Gibbs-preserving maps, say, or resource theoretical formulations where the interactions matter at the end of the day, where you could actually compute things that would not have to involve all degrees of freedom, but only a small number of degrees of freedom at the end.
I would say this is what we do, but
yeah. Okay, but this is a computable expression. It's a kind of integral expression. This is kind of a nice thing. So there's a neat upper bound of this, which is if you just say what is the largest way these penalties can be, the largest value these penalties can have, we see that there's this one-size-fits-all upper bound in terms of the operator norm of the interaction, which is just the largest eigenvalue of all the individual coupling terms together, which in fact for a reasonable local interaction in the many-body problem would be just like the boundary area of a certain region and not like the volume, like not extensive. So asymptotically it would be a small, negligible contribution in the macroscopic limit. So that's kind of nice that for a given fixed coupling strength, if you go for large systems to the macroscopic limit, this contribution would become negligible and you recover the standard weak coupling limit in the setting of fixed interaction strengths in the macroscopic limit, which is cute. There's also another setting which can be completely fleshed out, and that's the last thing I say about this, is one can in fact go a very long way if one accepts, or actually completely solve the problem, if one accepts a perturbative approach by saying that the coupling, and that relates also to your question, that the coupling is of the type G times V, where one can do like perturbations, that's actually surprisingly technically involved, but looks at perturbations of these relative entropy expressions and sees whether this perturbation in the interaction can be computed altogether. And this, in fact, can be completely fleshed out and laid out in a nice fashion so that you get very simple and easy expressions. I mean, this may not look so simple, but here the point is that these penalties that kind of give the expression of the maximum work extraction in the strong coupling regime would just be covariances, so correlation functions of renormalized coupling Hamiltonian terms in Gibbs states of the non-interacting Hamiltonian. So you only have to compute correlation functions to, in leading order, compute the strong coupling corrections for weak work extraction in the strong coupling regime. That's kind of cute because this is a setting that can be basically computed for all Hamiltonians. Just compute correlation functions and you have in lowest order the expression in perturbation theory. It's kind of a cute workhorse to deal with arbitrary Hamiltonians of this type. So I'm stressing so much that this is like a model independent and general bounds for arbitrary Hamiltonians as such, but of course it's nice to keep sort of contact with reasonable settings and models. So this is the ubiquitous model in optical mechanics or in quantum thermodynamics of quantum Brownian motion, so the Caldera-Leggett model for quantum Brownian motion, where we see the expected work extracted as a function of the coupling strength, where the blue dots are the exact dynamics of the full analytical solution of the problem. The curve on top of that would be the one where we do the replacement. That was your question, of just replacing the state with the reduced state of the global Gibbs state. So this is just on top of each other, thus giving further evidence how right that is. The blue curve is the upper bound derived. It's quite tight. It's a bound, but it's quite tight. And the yellow curve is the recoupling limit, which is completely off, because there are these strong coupling corrections, and this is what it is. So to cut a long story short, strong coupling has a significant influence on work extraction. It's not a feature. It's rather a bug. It's a burden. So there's less work you can extract in this setting. One can go a long way to a complete answer to the problem in terms of these kind of Duhamel formula type integrals for arbitrary Hamiltonians. This involves a small number of degrees of freedom in the high temperature limit, and in the recoupling setting, in the setting of perturbative approaches, one can really hammer down the problem in all generality of just solving the problem to at least to lowest order. Good. So I've spent relatively much time on this, and I will just kind of go over a couple of implications of this in a more superficial fashion, but I think it's clear how this comes out at the end of the day. So clearly one can, using this kind of framework, one can think of dissipated heat, Landau principles. One can think of the efficiencies of thermal machines, say operating at two different inverse temperatures heat baths, and then thinking of strong coupling interactions to these respective heat baths. And then one can indeed again show corrections to this Carnot efficiency, which I don't state in full glory, but I mean they follow from this formalism where again there's a burden, this is a limitation, there's less work one can extract given the strong coupling setting compared to the recoupling limit. And indeed, again, in lowest order the perturbative contributions vanish, that's good news, it's stable, but in the next leading order this can be all computed again in the framework of correlation functions, pretty similar to the way I've just laid out in the previous setting. So maybe unsurprisingly, strong coupling is a burden. It's a limitation to work extraction and efficiency compared to the weak coupling limit. So how about power? Does strong coupling help? Does it become easier, better? So power is a bit delicate because for a given model, of course, time comes into play, and you can solve the model and see how the timing comes in. But even though I was insisting on all these rigorous insights onto thermalization, equilibration for arbitrary Hamiltonians, that's all beautiful and nice, yet the least thing that's understood is time scales of equilibration of arbitrary Hamiltonian models. There's a bit of a downside that we have very little understanding of how fast systems would ultimately equilibrate and thermalize. But what one can do as a crude upper bound, one can just lower bound the time it takes to equilibrate by the energy exchange of the bath during equilibration, and just the operator norm of the commutator as a worst case bound, how quickly one can dissipate energy to the environment as a bound that's clearly tight for a given specific Hamiltonian, but that might be not super tight for a given Hamiltonian that you happen to have. But that's the best bound one can formulate if one wants to have a general bound of this type. And indeed, using this, one can formulate rigorous upper bounds on power that would be applicable to all Hamiltonian models, which are limited in this way that there are limits to power in these work extraction schemes in the setting. Again, one can also do this perturbative setting. I'll be brief here. One can find this lowest order expression following the framework as I laid out. There's the lowest order contribution that is linear in the coupling, meaning for very small coupling, there's very little power. You increase the coupling, there's more power, it's better. There's more power coming out, and for more coupling still, there's a leading contribution. So for very large G, that's your question, that for very large coupling, again, this would go to zero, there's no power whatsoever at all. So there will be a maximum in the middle. There's very little power at the beginning, and it will grow, and for large times for large coupling, it will go to 0 again. So this is how it looks like for ohmic dissipation in the quantum Brownian motion limit. So again, it will be small. There's a maximum in the middle, and for very large couplings, the power would again go to 0. In fact, that's not just a feature of this thing. This can be always true. In this sense, Oscar Wilde is being challenged here that everything in moderation, including moderation. That's not quite the case, because here indeed, not the smallest power, but some kind of intermediate value of coupling is the best way of maximizing the power in the setting. And this would be always the case, that the power is somewhere in the middle and not at very small and not at very large, but at some intermediate value of the coupling in the strong coupling setting. Oh, well, not really. It rather proves that he was wrong, although wow. That is a bit of would be not attempting to prove anybody anything about Oscar Wilde. He's kind of my hero. Anyway, so optimal power is obtained for finite coupling strength in the setting. There's a finite value where power can be maximized for an intermediate value. So this brings me, there's a final point I would like to make on this, which is strong coupling is often associated with kind of non-Markovian features in the setting of like Markovianity effects of the system and the bath coming into play. Like mathematically speaking, a process is Markovian if there's a dynamical semigroup law behind it. Physically speaking, a system would be Markovian if if the interactions and the correlations of the system and the environment would be of the type that these correlations and these would never come back to the dynamics of the system, so that the dynamics is forgetful in this fashion. So recent years have seen a huge body of quantitative work, not only arguing that a process would be Markovian or not, but arguing how much non-Markovian a process would be in quantitative terms. And the cute thing here is that this can be related to notions of divisibility and information backflow and so on. The cute thing here is that the examples I kept mentioning of ohmic dissipation in the quantum Brownian motion limit happens to be of the type that for small coupling one indeed also in this quantitative fashion recovers the precisely Markovian limit of the setting. So what we are probing here with this strong coupling limit beyond this kind of small weak coupling expressions would not only be the strong coupling setting, but also in quantitative terms probing how non-Markovian the dynamics would be. So the Markovian point is precisely this kind of ohmic weak coupling limit, so that the strong coupling probes deviation from Markovian dynamics in quantum Brownian motion. So the strong coupling limit we are talking about is also precisely the non-Markovian limit in quantitative terms, and you can tune from the Markovian limit to the non-Markovian limit in the setting, again seeing how strong coupling and Markovianity kind of nicely come together and form one picture. Good. So 33 minutes into the talk. This was everything I wanted to say, although if I have 7 minutes left, I would kind of meditate a little bit at the end, or maybe 5 minutes to keep some time for questions. There were already many questions. Okay, so let's summarize. So what have we looked at? It was a very basic question. We looked at the implications of not having weak coupling limits, but strong coupling in quantum thermodynamics, where the interaction will matter, where one cannot expect the system to thermalize, but at best the global system to thermalize, so that the reduced state would look as if the entire system would have thermalized to a global thermal state. That's a very reasonable setting in the strong coupling setting, and we've already also seen that this can be rigorously proven, at least in the high temperature limit, that this very natural assumption would even be true in this very quantitative sense. But it could go a long way of actually solving the full problem in a closed form expression, even in strong coupling. This involves funny integral expressions, but they can be computed in the high temperature limit, indeed only involving a small number of degrees of freedom, which is cute, because one can actually, even for funny Hamiltonians, do this this type of calculation. This is a nice thing that goes as long as it gets towards a general solution for arbitrary Hamiltonians of that type. But we've seen also that that if one accepts a perturbative approach, then one can pretty much hammer down the problem as just solving correlation functions in an uncoupled Hamiltonian. That's cute. So in perturbative treatments, one can just solve the problem, which is nice. And also these notions of equilibration and thermalization came into play to justify the setting in what very strong coupling comes into play. So this is a kind of a setting how this goes. So this might be a very nice setting also like in experimental considerations to see how correlation effects matter, say in systems of trapped ions, it maybe or at V centers, this might be a nice vehicle to see how correlations matter and how notions of work extraction schemes are changed in the presence of strong interactions, which can be quantum because these terms are not necessarily commuting. So this might be a relatively simple, nice setting that could be explored in experimental settings. A setting that was even more experimentally motivated, actually by Jörg's experiment, was to look at work extraction schemes in which not only single but more, even many additional charges would matter. So the equilibration language, there would be a kind of generalized Gibbs ensemble so that in integrable models, systems would not fully thermalize, but would only thermalize as much as they can to be maximum entropy states given these additional constants of motion. This could be a cute setting in the sense that work extraction is limited, but one can look at the work extraction schemes or quenches in these close to integrable models as a kind of an interpretation of almost already existing settings where one can read these quenches to integrable points in the framework and language of quantum thermodynamics, which would be a nice setting of using this to relate the abstract formalism to actual experiments. At the same time, there's no denying that much of the excitement of the field also comes from the fact that we are here at asking these basic questions on basic, like where quantum statistical mechanics comes from altogether, where ensembles, how ensembles come about in the first place, and there's some kind of cute paper, what I was quite excited about recently, that would derive like the statistical ensembles not from using the Jane's principle or invoking notions of typicality, but just by looking at states that can be reached in an operational way from systems where one only has partial information about the preparation of the system. And finally, this is a work that has not come out yet, but one can ask the cute question whether environments in quantum thermodynamics actually have to be large. It's always this kind of common assumption that there's this large environment and a small system that would thermalize in contact with the bath, but one could ask, how small can environments actually be to thermalize a quantum system? And they can be actually surprisingly small to equilibrate and thermalize a system. So if one, actually a square of d dimension would be sufficient to thermalize or equilibrate an arbitrary quantum system, if one accepts equilibration and thermalization in 2 norm, even a constant dimensional bath would be sufficient to thermalize an arbitrarily large quantum system, which is kind of a cute thing, that very small baths in this sense can thermalize arbitrary large systems. So I'm just saying this as a kind of teaser for the coffee break, that there are these kind of fundamental questions sitting around in quantum thermodynamics, like on where these ensembles pop up, what small environments can be, but well, this is just a kind of teaser for the coffee break. So here's the kind of the lesson again on a talk on limits and potential of work and power in the strong coupling regime. And with this, I would like to thank you very much for your attention.
Well, question.
Yeah.
Are these results valid for any coupling operator between the system and the bath, or you are assuming specific forms?
Oh, that's a good question. Oh, the question is whether I'm assuming anything about the coupling or whether it's true in all generality. It's true in all generality. There's nothing assumed about the system. It's specifically, this general expression I mentioned is not making any assumption whatsoever about the coupling. The other questions, the perturbative approach that I mentioned are also general, but it is what I said. It's a kind of a perturbative approach. But otherwise, there's no assumption whatsoever on the interaction. Yeah. Oh, so many questions. That's nice. Yeah.
So you had this statement that strong coupling is a burden to work extraction.
Yeah,
Is
indeed.
that in the context of a quantum calculation,
Yeah.
would you expect the same would be true in the classical case? And
Oh,
so-
that brings me back to this question, because since it's true for arbitrary Hamiltonians, I can perfectly look at diagonal and commuting Hamiltonians, and the same would be true there. Yes.
So is there a good physical intuition there? Why should we expect strong coupling to be a burden?
Oh, I mean, what is intuitive for one is not necessarily intuitive for the other. I mean, ultimately it's, I mean, the thing is that if you, there's always kind of heat dissipated, and the state is always kind of wrong. When you put a system in contact with a bath and it jointly thermalizes, then there's always some dissipative effect when you bring it into contact, and this is very hard to make reversible in the same way as you can make the recoupling setting reversible.
Okay, so it's
That's kind
associated
of,
with the turning on of the...
this is a large contribution that will matter and will come into play. I mean, of course, you have to look at arbitrary schemes. You don't have to do it, but there is not really a way of avoiding that type of effect. That's kind of the insight. Oh, nice.
Question back.
Yeah, yeah,
That's somewhat related question. I can take arbitrary strong coupling system.
Yeah.
Reduce density matrix of
Yeah.
the system.
Mhm.
Define it b minus beta effective Hamiltonian.
Mhm.
And say I actually have a deep coupling with this new effective Hamiltonian. So and then I can say that any strong coupling theory is just completely equivalent to some other deep coupling theory. But why is it important for the work? So what makes this new Hamiltonian special?
Okay, I'm not fully sure I understood every detail of the question, but I will answer it to the extent I think I've understood it. I mean, here, this is completely general and true for arbitrary Hamiltonians, except that you would make some choice at some point what you think your system is and what your environment is. So in this sense, there's a choice of, this is my system, this is my coupling, and this is the environment. And then this strong coupling of what I think is the system and what I think is the environment, this will matter. Of course, one can think of a larger environment, or of the system and part of the environment forming a kind of a new system. Is that what you said? And this.
Yeah, this is possible, but that's not what I said.
Oh, okay.
Just take reduced density matrix of what you call system
Yeah.
and say it's equal to minus beta effective. It's
Oh
like-
yeah, this is so done all the time. Yeah, indeed.
Right. So, but why? And then you say it's a deep coupling to a different Hamiltonian. But why?
No, but this is something.
No, I'm completely.
Yeah. No, indeed. Of course. Well, there's a slight misunderstanding here in the sense that, of course, you can do that. If you reduce state, there's always this, well, it's thermal Hamiltonian, so that there is a Hamiltonian such that this dude is just the Gibbs state of that new specific fictionist Hamiltonian that's also used all over the place. But that doesn't prevent you from having correlations to the actual environment of the system. So this will be there, and this will have an impact. That's something for the coffee break. But, of course, this is true that you can find some Hamiltonian, but this will not prevent you from having effects from the correlations with the environment. Let's discuss this. Yeah. Yeah.
I think there is
Yeah.
a simple picture, and it can be done for exactly solvable models,
Yeah.
like spin boson system.
Yeah.
You can kind of dress it. If you start with a product state, it has always larger energy than the dressed
Oh, this is a
state.
beautiful picture.
So
Yeah.
the rest of the energy dissipates.
Beautiful picture. In fact, another solvable model, I just hinted at that, this Brownian motion model would be of that type. It's also analytically solvable, and this dressed picture would precisely emerge there. It's a nice, beautiful picture. In fact, in some appendix, we've even elaborated on this dressed picture to an extent. That's a very beautiful, that's an intuition that we share. Yeah. Oh, yeah, Chris.
I was wondering, for the perturbation theory, what's the relevant energy scale you're comparing to? The temperature or some quantum, like, for a system? What's describing the system? Because typically, as you cool it down, quantum effects will play a more important role than temperature or something like this. So can you...
Okay, I have a mathematical answer and a physical answer. The mathematical answer is, this is actually pretty cute. There's a kind of some insights into perturbations of quantum relative entropies. What it really is you have G times V, and you just count quarters in G. And this is what it is. And then you can say, how does it relate to quantities in the system? It would be somehow that the relevant energy scale of the coupling would be small compared to the energy scale of the bath. Indeed, that would be the natural setting in which this is natural.
So it's not temperature?
It's not temperature. No. Yeah.
So I guess my question is related to this one. When
Yeah.
you show that the power has this crossover and there's an optimal
Yeah.
value, can you explain physically what dictates this optimal value in the interaction?
Oh, as often in physics, you could say a lot about little and little about a lot. Meaning, no, this is actually true very, very broadly. I mean, say in the quantum boundary motion model, which is a beautiful model, and that's all the glory. Of course, it's a very simple analytically solvable model. I have a very good intuition where this happens, and you can give even intuition where, why, and there's one maximum and so on. For arbitrary models, for whatever crackpot interaction, this will also be true that for very small couplings, power will be small. For very large couplings, again, it will be small, and there will be a point where this is large. This is still true. But of course, one cannot expect if you take some fractional quantum Hall thing coupled to some edge mode of whatnot, and then make a sudden quench that there was some maximum. Whatever, there could be something funny. So in arbitrary models, there cannot be intuition whatsoever on when this happens. But there's good intuition why it's small for small system, and that the perturbation theory shows that it will be linear in leading order in G. So for very small coupling, it has to be upper bounded by a linear slope, which is good to know. So this can at most go like this. And for very large coupling, there's also good reason why it will just hammer down the power, because then that relates to your question of V being, in principle, arbitrarily large. You can have a setting where the interaction is so strong that it just hammers down any other scale in the system. That basically it's just interaction, and the rest is completely negligible. That's a meaningful setting. And in this setting, you get a good intuition why power is dead. There's no way you could get power out of this.
One last question, and I get it.
Oh!
An intriguing area of future quantum thermodynamics is entanglement entropy, mutual entropy.
Yeah.
You look at the entropy of the whole thing and you take it apart, and boy, they're not the sum.
Oh, yeah.
And it turns out that there are some intriguing results of that, which I will mention in my talk tomorrow. But that combination of ideas together with strong coupling would be a fruitful area for research.
Oh, I couldn't agree more. In fact, I even had a slide on this, which I took out for reasons of time. I elaborated a bit on this when I said that as the upper bound for strong coupling, there's kind of this area law-like prescription that the strong coupling effects will be negligible in the macroscopic limit. There is precisely for the mutual information that you mentioned, like the global entropy, like the entropy of the subsystem, plus the entropy of the bath, minus the global entropy, that's this mutual information, the correlation measure that you mentioned. This would also have this kind of area law feature for arbitrary temperatures, and this can be related to this kind of area law-like fashion of free energies. I mean, we've made baby steps in that direction. I mean, by no means it's a full picture, but I mean, this is a very interesting question, and in fact, we made a bit of a baby step in this way.
Let's thank our speaker again.
Okay, thanks for that.